Hi and welcome to John's Maths Book. In this video, we'll be exploring another key concept in mathematics. If you find this tutorial helpful, then please show your support by subscribing, liking, and leaving a comment. Your positive engagement helps me create more content and allows me to bring you more valuable maths lessons. Without further ado, let's go over to the whiteboard. Let's look at the properties of an ellipse and then prove that its area is equal to pi AB. I've drawn an ellipse on the whiteboard centered at x equals 0 and y equals 0. The equation of this ellipse is x squared divided by a squared plus y squared divided by b squared is equal to 1. And in this case, a is greater than b. The distance along the x-axis of the ellipse is known as the major axis, and the distance from the center of the ellipse along the x-axis is known as the semi-major axis. Similarly, the distance along the y-axis of the ellipse is known as the minor axis, and the distance from the center of the ellipse along the y-axis is known as the semi-minor axis. There are two special points on the major axis of an ellipse, shown here as F1 and F2, and these are known as foci. The sum of the distance from the foci to any point on the ellipse is equal. So that's the sum of d1 plus d2. So as we move around the ellipse and pick different points, the sum of the distance from the foci is always the same. Before we look at the proof of the area of an ellipse, let's look at the equation once more. Let's now suppose that A equals B, which in turn is equal to R. If we substitute R in for A and B, the equation becomes x squared plus y squared divided by r squared is equal to 1. And therefore, x squared plus y squared is equal to r squared. And as you can see, this is the equation of a circle centered at 0 with radius r. So a circle is a special form of an ellipse where the two foci coincide at its center. So the foci of a circle are located at the same points. One further point to note about the equation of an ellipse is that if the ellipse is centered at some point other than x equals 0 and y equals 0, so let's say where x equals h and y equals k, then its equation is x minus h all squared divided by a squared plus y minus k all squared divided by b squared is equal to 1. So now let's prove that the area of an ellipse is equal to pi AB. So if we subtract x squared divided by a squared from both sides of the equation of an ellipse, we get y squared divided by b squared is equal to 1 minus x squared divided by a squared. This simplifies to y squared divided by b squared is equal to a squared minus x squared all divided by a squared. And multiplying both sides of the equation by b squared gives y squared is equal to b squared divided by a squared multiplied by a squared minus x squared. So the equation of an ellipse expressed in terms of y is y equals plus or minus b divided by a multiplied by the square root of a squared minus x squared. And so y equals b over a multiplied by the square root of a squared minus x squared represents the portion of the ellipse above the x-axis. Similarly, the portion of the ellipse below the x-axis is represented by y equals minus b divided by a multiplied by the square root of a squared minus x squared. So to find the area inside of the ellipse, we can subtract the integral from minus a to a of the equation of the ellipse below the x-axis, giving us the area shaded in red, from the integral from minus a to a of the equation of the ellipse above the x-axis, giving us the area shaded in blue. So the two negatives here make a plus. So we have 2b divided by a multiplied by the integral from minus a to a of the square root of a squared minus x squared dx. If you've been watching my other videos, namely this one, which I'll drop a link to in the description, you'll see that this integral here evaluates to 2b divided by a multiplied into the bracket of a squared sine to the minus 1 of x over a all divided by 2 plus x multiplied by the square root of a squared minus x squared divided by 2. So now, if we plug the limits of integration into this, so starting with x equals a, we have 2b divided by a into the bracket of a squared multiplied by sine to the minus 1 of 1 all divided by 2 plus a multiplied by the square root of a squared minus a squared all divided by 2. And we need to subtract from this what we get when we plug in the lower limit of integration, which is x equals minus a. So we have minus 2b divided by a into the bracket of a squared multiplied by sine to the minus 1 of minus 1 all divided by 2 plus, and then we have minus a multiplied by the square root of a squared minus a squared all divided by 2. And so simplifying this term and this term both evaluate to 0, so both eliminated. Sine to the minus 1 of 1 evaluates to pi by 2, which we multiply by a squared divided by 2 and then further multiplied by 2b over a. This evaluates to pi ab over 2. And sine to the minus 1 of minus 1 evaluates to minus pi by 2, which we multiply by a squared over 2 and then further multiply by 2b over a. And this evaluates to minus pi ab over 2, which we subtract from pi ab over 2. The two negatives become a positive, and this gives us a final answer of pi ab, which is the area of an ellipse.